Hi guys, this is lecture 10. In lecture 9, we studied the main statistical estimators that we use in probability and statistics. We studied the mean, we studied the median, and we studied the mode, and we studied the variance and the standard deviation. So the mean is generally indicated with the Greek letter mu, and for a discrete property is the sum over all the outcomes of the outcomes times the probability of the outcomes. And for a continuous property, this is just the integral of x times the probability density function in the x. The median is simply the value such that the cumulative distribution function is equal to 0.5. So it means that you have 50% of chances of, or 0.5 probability of having values below the median, and 0.5 probability of having values above the median. The mode is just the most likely value, so it's the value such that I guess we can formalize it as the max or argmax of the PDF, or the PMF in the discrete case. So the max, I hope you remember the difference between the max and the argmax. If you have, well, in this case we have a probability density function, but it can be any function. Well, x tilde is the argmax, and the value of the function in x tilde is the max. So what we care about is the value of the random variable, so on the x-axis. So it's the value such that the function f reaches the maximum. And then we saw the variance and the standard deviation. Well, again, the variance is sigma square, and for, well, I should say discrete property here and continuous property here. Again, we're going to do both cases for the variance. It's the sum over all the xi of xi minus mu of x, what we call the residuals sometimes, times the probability of xi. And then for the continuous case, it's the integral of x minus mu of x times the PDF of f of x, the PDF f of x in the x. Well, and we saw some simple examples where we actually computed the mean and the variance. So for example, we look at the exponential distribution. Lambda power times e power minus lambda t for t greater than 0, greater than or equal to 0, and then 0 otherwise, which is essentially a probability density function with high likelihood for values close to 0, and then the likelihood converges to 0 for x that goes to infinity, and then it's 0 otherwise. Well, we saw that we could compute the mean, mu of t, which is equal to 1 divided by lambda, and the variance, which was equal to 1 divided by lambda squared. Now, you don't have to do it for the most common PDFs. I will give you some the parameters every time we study some PDFs. But it's important to see how they can be computed once in a while. There is actually a statistical parameter that is not commonly used in geoscience, but that could be useful. It's called the coefficient of variation. It's a unitless measure of uncertainty, and it's given by, we generally use delta, so we have x, a random variable, and delta of x is the standard deviation of x divided by the absolute value of the mean. This is kind of useful for comparing random variables with different means because, again, it is unitless. Now, if you think about it, if you look at the statistical estimators that we commonly use, let's say that we're looking at something that represents a length. So let's say that the random variable x is in meters, then the mean of x is going to be in meters, the variance of x is going to be in meters squared, so the standard deviation is going to be in meters as well. So if you take the standard deviation divided by the mean, or the absolute value of the mean, this is unitless. Now, it's not useful when the mean is equal to 0, of course, because you cannot define it. But this is a property that from time to time in other fields is commonly used. I just wanted to mention it. There are some other parameters that we might be interested in using. I'm not going to give you the definition because it can be kind of painful, but I'm just going to give you an intuitive idea of what they are. Now, in general, what we can do is define the so-called moments of a random variable. So we indicate them with E, the random variable power m, and that's just by definition the integral of x power m times the probability density function, and m can be any integer. So this is called the mth moment of the random variable x. And the first few moments, they provide useful information. Well, the first one is actually the mean, as we have seen. We also have what we call the central moments. So in this case, we take the random variable minus the mean, power m, and those are called the mth central moment of f. Of the random variable x. Now, the most common one is the variance. So when m is equal to, we obtain the variance of the random variable x. Well, this I'm just going to give you the definition again. This is a little bit more on the theoretical side, but in case you hear the names, I would like you to just be able to read the paper and understand what they're talking about. This operator here is called the expectation, and in general, you can define the expectation of any function of a random variable. It's just the integral of the function, the PDF, times the function of the random variable itself. So this is the PDF, and this is any function g that you want to apply to the random variable. well, again, if we take g of x equal the random variable, we obtain the mean. If we take x minus the random variable minus the mean, a square, we obtain the variance, and so on and so forth. So for g of x equal x, you obtain the mean. For g of x equal x minus mu of x square, you obtain the variance, and so on and so forth. Now, in theory, you can derive as many statistical estimators as you want. In practice, we generally use just the mean and the variance. And now I'm going to introduce a couple that you might hear from time to time. I just want you to have a general understanding of what they are. Now, there's one important consequence from that, is that the mean is actually linear, is a linear operation. So if you take the mean of the sum of random variables, it's the sum of the means. So if I use the notation ex plus y, this can be written, so this is the integral of x plus y. Well, I'm not going to prove it, but this is just the mean of x plus the mean of y. Or if you want, you can write it as a linear combination. Let's say e of a plus, let's say that we only have one random variable for simplicity, and we do an operation in the form, we multiply by a scalar and then we sum another scalar. Well, this is a plus b times the mean of x. Or if you want to use the notation mu of ax plus of a plus bx, this is a plus b times mu of x. That's just for the linearity of the integral. But then if you take the variance of a constant times x, well, this is the expectation of c x minus c of mu of x square. This can be written as e c squared times x minus mu of x squared, which is c squared times e, the expectation of x minus mu x squared, which is c squared times the variance of x. So the variance is not linear. If you multiply a random variable by a constant, the variance of the new random variable is going to be the square of the constant times the variance of the original random variable. So essentially, in the short notation, sigma square of cx is equal to c square the variance of x. If it was linear, it would be c. Okay, so this is just an important detail. This is important when you try to rescale or normalize variables. The variance doesn't scale linearly. We also have two other moments that from time to time we hear about: the skewness and the kurtosis. Well, we're going to do the kurtosis in a minute. So the skewness is generally, we generally use gamma, and this is simply the integral of x minus mu x, the mean of x, cubed times f of x in the x. This property here measures if a distribution is skewed to the right or to the left. Like this distribution here would be skewed to the left. This distribution here would be skewed to the right. So if gamma is positive, it means that we have a long tail to the right. And then gamma negative means that we have a long tail to the left. So for example, if we look at the exponential distribution, well, this one here, the gamma is equal to 2. So this is positive, which means that we have a long tail to the right. So the distribution is skewed on the left. Indeed, if I try to plot it, here we have a long tail on the right, and most of the values, the more likely values are concentrated on the left. I'm not going to do this computation here because this integral here can be kind of tedious. We also have the kurtosis. Essentially, we just take the fourth central moment. And this one here somehow describes how squeezed and stretched the distribution is. I'll give you an example with two distributions that have the same mean, the same variance, and the same skewness, but different kurtosis. I'm going to try to draw them. So here we take some sort of Gaussian distribution, something like that. If I take I can take a distribution that is more compressed here on the y-axis, but then the integral has to be 1, so it's going to go to the tails quicker. Well, it's not a very impressive drawing, but these are two distributions with the same mean, the same standard deviation, or the same variance, and the same gamma, but they have different kurtosis. We're not going to use this property, but just in case you hear the name, it's important that you know at least some sort of intuitive meaning of it. And again, this is kind of hard to compute, so we're not going to do it. Now, in the same way, so you remember that we look at PDFs, but then we also look at joint PDFs. So what we're going to do now is joint moments of random variables. We're only going to study one moment, which is the covariance. So if we have multiple random variables, we would like to study the moments of one random variable, the moments of the other random variable, but we also would like to study some kind of statistical property that describes the relationship between the two. And this property here is the covariance. Now I'm going to give you the definition. So it's generally so we have two random variables, x and y, and then the covariance, we still use the symbol sigma, but in this case it's sigma subscript x and y. Well, this is simply the expectation of the random variable x minus its mean times the random variable y minus its mean. So this is the integral, the double integral of x minus mu x times y minus mu y times the joint distribution f of x, y in dx dy. So if you want, you can skip this intermediate step because you already know how the expectation operator works. This is just the function that we multiply the PDF before integration. So the covariance is the double integral of the residuals of x times the residuals of y times the joint PDF. Now, the covariance is a measure of the linear dependence between two random variables. I'm going to show you in a minute what this means. It's going to be more clear when we do some examples. Unfortunately, the statistical and the probability notation sometimes is not very intuitive, but dependence. So it's a measure of the linear dependence between two random variables. Now, if we take the covariance of x with a random variable x with itself, then we get the variance. So if we take sigma xx, this is the double integral well, we're only integrating over x, of course, of x minus mu of x squared times the margin distribution of x. So this is equal to the variance. And the same for y. This one here sometimes is also written as covariance of x and y. Now, if we have two random variables, we often represent covariance and variances in one unique object, which is the covariance matrix. So we generally use sigma of x, y, and this is the variance of x, the variance of y in the diagonal, and the variance of x and the covariance of x and y. Now notice that this one here is the same as the covariance of y and x because of the commutative property of the product. So this one here is actually a symmetric matrix. By construction, since you have variances on the diagonal, this is also positive definite. Most likely you're going to estimate this kind of covariance matrices from the data. So unless you have something, some numerical effect due to maybe data close to the precisions of the machine, these properties are always going to be satisfied. It might happen in some very particular cases that you estimate the covariance matrix from the data. We're going to see how to do it from the data in the next lecture. But or maybe, well, we're going to see something today probably if we have time. Sometimes when you have large data sets and you deal with properties, for example, on a logarithmic scale, so you get close to and for whatever reason, you get close to the precision of the machine, there might be some numerical effect in the computations that makes this matrix non-positive definite. So what I generally do, for example, is I add a little bit of random noise, and that gives you a positive definite matrix. But these are numerical issues that you only deal with when you have to work with large data sets with large noise and so on and so forth. Now, there is another important property that is probably the most important property in practical applications when we deal with multiple random variables, and it is the correlation coefficient. Now, the definition is we generally use rho of x and y, and this is the covariance between x and y divided by the standard deviation of x and times the standard deviation of y. Now, by definition, this quantity here is in between -1 and 1. You can actually prove it. I'm not going to do it, but if you are a little bit of statistical geeks or mathematical geeks, you might want to know the reason. So the covariance x and y is less than or equal to the square root of the variance of x times the variance of y. This can be proven using Cauchy-Schwarz. I never remember how to spell Schwarz. I think it's SHWARTZ. Maybe there's not a Z. Well, anyway, this is due to this can be proven using the Cauchy-Schwarz inequality. So this is less than sigma x times sigma y. We don't have to prove it, but remember that the correlation coefficient, which is probably the most important property when we look at joint random variables, it's always in between -1 and 1 included. This is a dimensionless measure. It doesn't matter if the property is in meters or centimeters and so on and so forth. And it measures the linear dependence between x and y. I'm going to stress a lot on the linear part, and I'm going to show you examples because sometimes, what did I do? Sometimes correlation is used in common English language, but in statistics it has a specific meaning, and we're talking about linear correlation. So we're going to see exactly what that means in a minute. Let me finish the sentence. It measures the linear dependence between two random variables x and y. So if rho x y is equal to 0, the variables are uncorrelated. If rho x y is equal to 1, then they are linearly correlated with plus or minus 1, let's say. Then they are perfectly correlated. In case, well, let's write it in this way. So if the absolute value is equal to 1, they are perfectly correlated. We're going to see the meaning in a second. Now, let me write a couple of notes, and then we're gonna draw some different cases where we can see what this means in practice. So if x and y are independent, then they are also uncorrelated. Remember that if x and y are independent, it means that the joint distribution can be written as the product of the marginals. So this is what independent means. Now, let's try to understand the difference between independence, dependent and independent variables, and correlated and uncorrelated variables. I'm trying to find the examples in my notes. Okay, here. Okay, we have, I'm going to draw a bunch of different cases. So I'm going to draw some random samples, and then I'm going to draw the joint distribution using the contour plots. So if I have a bunch of data like this, and I try to put a joint distribution, well, this is approximately how the contours will look like. So this is a case where the correlation is equal to 0. If I have dots that are aligned along where we can see a clear relationship, then the joint PDF is going to be something like this. Now, this one here is a case where we have correlation greater than 0. This could be something like 0.8. So somehow the data are aligned along this line here. Well, now if the straight line has a negative slope, then the correlation coefficient is going to be negative. So this is the case. This would be the case, for example, between density of a rock and porosity of a rock. So this is a case where we have negative correlation, say approximately minus 0.75, for example. And this is the case between porosity, this is velocity, and velocity. Well, I gave you this example before. I'm going to give you another one. Generally, let's see, if the porosity increases, then the volume of clay decreases. So this is an example in a mixture of sand and shale. If you compute the clay volume, generally you have this kind of relationship here. Now, if you get exactly 1, so it means that the data must be aligned along a straight line. So this is, they're perfectly on the line. Say 0.99 if you put a little bit of error. So if rho is equal to 1 exactly, then it means that the random variable y can be written as a plus bx. If you actually try to compute the correlation coefficient of x and y, you're going to see that it is automatically equal to 1. Now, the important thing, so note number 2, is that if x and y are two uncorrelated random variables, it doesn't mean that they are independent. So typically you think about a case like the first one here, where you have two random variables that do not have a correlation, they're not aligned along a straight line, and you think that these random variables are independent. But I can show you an example of random variables where the correlation is equals 0, but they're not independent. If I take x and y like this, now the correlation coefficient here is approximately 0. However, these two random variables are not independent. They're clearly dependent because y is something in the form x squared, right? So this is a case where y clearly depends on x, because I can write some sort of analytical solution for that. But the correlation coefficient is almost 0. So uncorrelated does not imply independent, because uncorrelated only means that there's no linear dependence. So what the correlation measures is the linear dependence between two random variables. If it is 0, it means that there's no linear dependence, but there might be a quadratic dependence, there might be a logarithmic dependence, there might be almost whatever relationship you want. So again, the opposite is not true. So if x and y are independent, they are for sure uncorrelated. But the opposite is not true. I'm stressing a lot on it because sometimes in common English language we use the expression uncorrelated as independent as synonyms, but from a statistical point of view, this is not true. Okay, so far we have seen some sort of theoretical approach to random variables. We haven't used any data yet. So how can we use data to build a distribution for a random variable? That's going to be the scope for the next couple of lectures. In general, probability theory does not require any real data. But our geoscience applications of these tools, they usually requires us to use observed data when we create our models. So somehow we need ways to organize and present our data so that they can be used efficiently. This is generally what statistics is about. So remember that in the class I show you a couple of times this plot already. So we have observations of data. We have models of random variables. And we make predictions of future events. Now, if we know the PDF, then we can make predictions using, so these models are PDFs or PMFs. or CDFs, whatever you prefer. So we use probability to make predictions based on these PDFs. So far, we somehow assume that we know the PDFs. Like in this case here, for example, we typically use the mean to make a prediction. If I have a model for a random variable, for example, the distribution of the earthquakes or the distribution of velocities in the subsurface, seismic velocities in the subsurface in a specific region, well, we look at the PDF, we take the mean and or the mode or the median. This is the model that somehow we think is the best. The mean because it minimizes the error in the least square sense, the mode because it's the most likely, and so on and so forth. And that's our prediction for the next event, right? Typically what I do in my research is that I compute the probability, I collect seismic data, I compute the probability of porosity given some seismic data. So it's a conditional probability, say velocities. Now, this one here is going to have like a shape that is generally bimodal, so it might be something like this. And I take the mode as my statistical estimator. This is going to be my prediction. So this value here of porosity is going to be my prediction of the most likely porosity in the reservoir. I'm going to do it at different locations, but in general, that's the approach. That's what we do with probability when we make predictions. The problem, though, is that so far we assumed that we knew what the PDF was, and we computed the mean, the variance, and so on and so forth. Now, that's not what we do in practice. In practice, we get observations. So this is the part that we're going to look at now. We have observation, and we use statistics to build these models. The PDF, the CDF, and so on and so forth. So let's say that we have a bunch of data that we measure for example, an oil and gas reservoir or an aquifer. So we measure, let's say we have different locations, like different boreholes, for example, or different core samples. So location. We're just going to mark this location as 1, 2, 3, 4, etc. And then at each point, we can measure the velocity of the seismic waves and the porosity of the seismic wave. Of the rocks, sorry. So this one here is going to be a percentage or a number between 0 and 1. Well, let's put it as a percentage. And this one here is going to be in kilometers per second. So I'm going to put some random numbers. If I have porosity 30%, most likely the velocity is going to be around 2,000 meters per second. If I have 5%, this might be some close to 5,000. If I have 16%, it might be 3,300. 21%, well, let's say 4,300. If I have 21%, it's going to be 2,800, and so on and so forth. So I collect a bunch of data. Now, if we're only interested in velocity and porosity, what we can do is use histograms. So I can plot the porosity, for example. Let's say that we're looking at some kind of shaly sand in the rock, in the subsurface. So the upper bound might be something like 0.4, or sorry, this was in percentage. So 40%, and the lower bound could be something like 0. And this is the frequency. So this is the number of samples that are observed with that specific value. The histogram is a simple graphical tool, and it somehow illustrates the distribution of the data. The heights of the bars are proportional to the number of observations in the given interval. So this quantity here, let me try to make a nicer histogram. This was terrible. Okay, this is slightly better. So this quantity here, this is the bin size. So typically what we do is that we take the range of the random variable and we build a discretization. So for example, in this case, it could be 0, 0.5, it's a percentage. I'm not used to percentages, but I thought that it was easier to interpret. 5 and 10%, 10 and 15%, 15 and 20%, 20 and 25%, 25 and 30, 30, 35, and 35, 40. So these are the different bins. So the heights of the bars are proportional to the number of observations in the given interval. What we call the bin. So this gives an immediate impression of the most frequently occurring values and the range of the data, essentially. So the way we build the histogram, well, obviously the software, they do it for us, but we take a data set, we count how many times how many values we have between 0 and 5, and here we're going to list the frequency. So this is the number of values in the interval or in the bin. 0, 5, and we're going to do it for all the possible intervals. Like in MATLAB, typically there's a function that computes the histogram for you. Otherwise, what you can do is you do a for loop over all the samples, and you check if the sample belongs to the first interval, the second interval, and so on and so forth, and you count how many times this happens. It's one of the challenges sometimes is how to choose the intervals when we build a histogram. A rule of thumb is to take a number of bins that is 1 plus 3.3 times the log 10 of the number of data. Again, this is just a rule of thumb. What happens is that sometimes you plot an histogram and you get something like this. So you only have 3 bins for maybe a lot of observations because all the data are concentrated in the same region. And sometimes you plot an histogram and you get too many bins. So you get something really scattered, which is difficult to interpret. and then maybe if you find the optimal value, you can get a nice histogram that shows the distribution of the property. So sometimes it's just the structure of the data themselves, but sometimes it is useful to play a little bit with the number of beans such that you can get a nice shape and you can get a better understanding of the distribution of the property. So this one here is a good way to represent the distribution of the function, but sometimes we are more interested in the frequency distribution. So we take the number of observations in the bin and we divide by the total number of observations, and we get the frequency of the observation. So instead of plotting the frequency themselves, so for example, in this case, let's say that our initial data set had 100 samples. So we had 100 different locations. So I added one sample at the end just to show you how big our data set is. So here on the x-axis, we're going to get values like 10, 20, 30, 40, and so on and so forth. Well, this is too much, otherwise I guess we said we have 200. So let's say 5, 10, 15, 20. I'm not really sure if I reach 100. We can check. This would be, we have 5 samples in the first bin, 10 samples in the second one, 15. So we're already at 30. Plus 20, we get to 50. Plus, I guess this would be something like 17. Plus something like 13. So we get to 80. So I guess I have to add a couple here to get to the right value. Anyway, this is just a sketch. But on the y-axis, we have the number of samples in the beans. So that's what the frequency means, right? Number of values in the beans, or the number of samples. Now, sometimes you would like to get the frequency of the observations rather than the number of observations. So this is the number of observations. So if I want to have the frequency of the observations, what I can do is simply take the number of observations in the beans divided by the total number of observations. So essentially, you're just changing the y-axis. So I have exactly the same plot as before. But now if I normalize by the number of observations, what I get here are the frequencies. So this could be 0.05, 0.1, 0.15, 0.20. So this is obtained by normalizing by the total number of observations. Now, once we have the data, we can also come up with some sort of I call them numerical or statistical summaries. So we can compute the sample mean. Well, the sample mean is simply the sum of the observations divided by the number of observations. Well, you can also have the sample median, which is the middle value when you order the data set. So you have 50 values. In our case, we have 100 observations. We have 49 values that are below the median and 50 values that are above the median. The sample mode is not really, it's really poorly defined because it depends on the bin size. So we're not gonna do that. We also have the sample variance. Okay, now for the sample variance, we generally use the letter S because it means that it's estimated from a data set. So I'm going to use XX square, although a lot of people, they use sigma anyway. So in this case, we use mu, so let's use sigma, but it has to be clear that it's estimated from the sample, so from a data set. Now, in theory, the definition would be 1 divided by n times the sum for I that goes from 1 to n times xi minus mu x, the mean, square. In practice, we often use n minus 1 because somehow it's more stable. I don't want to enter in the discussion, but we say that it is unbiased in this case. And then we have the sample covariance matrix, the sample standard deviation. Which is simply the square root of the variance. Now, it's preferable to use n1 divided n minus 1 instead of 1 divided by n for, again, stability reason. It's actually because of it is unbiased, but some softwares, they might use 1 divided by n. So it's important to check the software when you compute the sample variance. Well, now, what we do, roughly speaking, is that let's say that we have our distribution of, let's see, well, let's use velocities of seismic waves in a specific layer. Well, this is our histogram. We can compute the sample mean, mu x, and the sample standard deviation, or the sample variance. Now, we can make an assumption, like this one here, for example, typically looks like a bell shape. So we can make an assumption and try to plot a distribution on top with the mean that we computed from the data set and with the variance that we computed from the data set. We're going to look how to do that. You could also take the histogram and apply methods that are called histogram smoothing, but Sometimes the function that you get is not easy to treat analytically. For example, if you have bimodal distributions, you could smooth the histogram in this way, or even more accurately. But we're going to see the limitations of this approach here. Typically what we do is compute a limited set of parameters and impose an analytical expression of the PDF such that when we plot the PDF versus some sort of normalized histograms, we get a nice match between the histogram and the PDF. In theory, you can also compute the sample skewness and the sample kurtosis to measure the heaviness on the tails and the asymmetric behavior, but you really need a large data set to get a reliable number. So most likely you will never do it. Well, if you have two random variables, you can also compute the sample covariance So it would be sigma xy. So we have two random variables, x and y. Well, this would be 1 divided by n minus 1 times the sum for I that goes from 1 to n of xi minus mu of x times yi minus mu of y. And then as a consequence, we have the sample correlation coefficient, which is the covariance sigma xy divided by the standard deviation of x times the standard deviation of y. And again, this is between minus 1 and 1. So that, in this case, the theoretical calculation from a PDF and the estimation from a dataset would give you, is still bounded between minus 1 and 1. And again, remember that, so if you have two data sets that are completely uncorrelated, you're going to get a cloud of points that looks like almost a sphere. So this has correlation equals 0. If you have, if they look like that they are aligned along a straight line with positive slope, this would be close to 1. If they are aligned along a straight line with negative slope, this would be approximately minus 1, close to minus 1, or we can say it. Yeah, let's put an arrow. So we are approaching plus 1 and minus 1. And then again, sometimes you have variables that are dependent, but the correlation coefficient is close to 0. For example, in this case, but there is a clear dependency because y is can be approximated by x squared. So we have already seen that with the theoretical approach. This is also true if you have a data set. So essentially, today what we have seen is the joint moments of random variables, so the covariance and the correlation coefficient. And then we look at which measures the linear dependence, not any dependence. And then we saw how to use empirical data to estimate some of these parameters, like the mean and the variance of a distribution, and also the correlation coefficient. So now the last step to try to build a statistical model. So we are working on this part of my big picture here. The last step is to look at a bunch of potential functions that could be PDFs or PMFs. And then once we get the data, we can estimate some parameters and we can fit some distributions on the data. So that's going to be the step for the next class. I'm not going to start today. I still have 10 minutes, but I think I went over the last couple of times by a couple of minutes. So we stop here. And then next class, we're going to look at the common probability distribution models that we can apply to repeated experiments. And we're going to look at discrete and continuous properties.